Part 2. What are the factors that affect speed of reaction? So now let's continue watching the video we watched previously.
Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Based on the videos, there were 5 factors that affect speed of reaction, but in our syllabus, we're just going to focus on the 4 factors that affect speed of reaction. Okay, so many factors affect the speed of reaction. So the 4 factors we're concentrating on is the temperature, concentration, pressure, and particle size. And when I go through these factors, I want you to bear these 4 questions in mind. The first question is, for temperature, we want to know how fast were the particles moving. Number 2, for concentration, we want to know how many particles were there in a per unit volume. Number 3, for pressure, we're looking at how close were the particles to each other. Then lastly, we're looking at particle size. So we're looking at how much is exposed. Okay, so these 4 questions: how fast, how many, how close, and how much is exposed. Now, first, let's look at temperature. How fast? So an increase in temperature increases the rate of reaction due to greater kinetic energy of particles, which results in higher frequency of effective collision. So greater kinetic energy would basically translate to faster particles. Okay, so when you increase the temperature, your particles move faster. Let's practice. Okay, so you are given 5 grams of calcium carbonate, okay, and 100 cm of hydrochloric acid, and it's added into beaker A. And this is kept at 25 degrees Celsius. In beaker B, everything's the same, but now the temperature is at 60 degrees Celsius. It's of a higher temperature. So use collision theory to explain the increase in speed when the temperature was increased to 60 degrees Celsius. So if you look at your notes, right, we've given you the criteria for success for this type of questions. So there are 5 points altogether. Point number 1. You should be able to state whether the particles absorb or lose energy upon heating or cooling. So in this case, you're increasing the temperature, so you're heating. So on heating, the particles absorb. Okay, so they gain energy. So you can either put absorb or gain energy. Point number 2. You should be able to describe the movement. Can you highlight? Of particles as they gain or lose kinetic energy. So when the particles gain kinetic energy, so this is linked to the first part. Okay, let me just change the color. Oh, where is it? Oh, I can't see it. Okay, never mind. Alright, if you look here, it's linked. Alright, so when the particles gain kinetic energy, they move faster. Alright. Third, you're able to state that the collision increase or decrease. So when they move faster, your collision will increase. If they move slower, the collision will decrease. So I will write it down here. You should do that too in your notes. So move faster, collision, increase. Slower, collision, decrease. Okay, pardon my handwriting, it's a bit ugly. Now, if you cannot read any of my handwriting, please inform your teachers and we can address the issue. Okay, so let's move on to the fourth part. I'm able to state that the frequency of effective collision increases or decreases. So when the collision increases, obviously, the frequency of effective collision will also increase. Okay, so this relates. Next, I'm able to conclude that this results in an increase or decrease in the speed of reaction. So this part you need to conclude. Okay, you need to answer to the question. So you're saying that increasing temperature will then lead to an increase of speed of reaction. Right, so how does temperature affect the shape of the graphs? If you allow the magnesium to react with hydrochloric acid but at different temperature, okay, I believe we're talking about calcium carbonate. So can we all change this magnesium to calcium carbonate? Okay, so if you allow the calcium carbonate to react with hydrochloric acid but different temperature, we will get two sets of results. So one is faster than the other. So graph 2 is faster than graph 1. Okay, so graph 2 is faster because a steeper gradient. Oops, can you see steeper gradient? And this is not. Okay. Alright. Graph 2 is steeper, so faster speed of reaction. That's why it's a higher temperature. So this is at 60 degrees Celsius. This is at 25 degrees Celsius. Okay. Next, how does temperature affect us? Okay, so how does this relate to our everyday life? Right, like I said earlier in the video in part 1, okay, we want to slow down certain reactions. So if I want to keep my food longer, I will keep the temperature lower. Okay, to slow down the chemical reactions or the decay, the process of decay in food. Now we're moving on to concentration. So the question we want to ask ourselves is, how many particles are there per unit volume? Because let us recall, let us recall the formula for concentration, or the unit for concentration. The unit for concentration is actually mole dm³. Alright, so essentially we're talking about the number of particles per unit volume. Let's move on. So how does concentration affect the speed of reaction? When concentration is increased, the rate of reaction will increase because there's more particles per unit volume of a solution, which then results in a higher frequency of effective collisions. So now let's practice. 5 grams of calcium carbonate powder was added to 100 cm³ of 0.5 mol per dm³ hydrochloric acid in beaker A. And in beaker B, you have the same conditions. The only difference now is you have 1.0 mol per dm³ of hydrochloric acid as opposed to 0.5 mol per dm³. So using collision theory, we are required to explain the increase in the speed when concentration was doubled. So again, on the right side, you have the criteria of success, which means what are we looking out for in your answer. So you should be able to relate the concentration to the number of particles per unit volume. So as the solution becomes more concentrated, more particles of reactants are occupying the given volume of solution. So I just want to write down here, when number of moles of particles increase, your number of particles will increase. Okay? And because there are more particles, the collision becomes more frequent. Right? So if you recall the video previously when you were watching, remember when the teacher tried to push in more students into the school? Okay, it becomes more crowded and more collisions happen. The same goes when we go for sales. Okay, not sure whether you would have gone for sales, but let's say you go for a sale, right? There's a lot of people. Then a lot more people will be knocking into each other, as opposed to when you go to the maybe shopping center at 11 AM. No one's there. So the likelihood of you colliding with somebody is very, very low. Because collision is more frequent, then the effective collision will be more frequent as well. So this will lead to an increase in the speed of reaction. Okay, so how does concentration affect the shape of the graphs? So again, you can see here, when your concentration is increased, okay, so this is actually beaker B and this is beaker A. When your concentration was increased, right, your gradient will become steeper because your speed of reaction is faster. Okay, but if you notice, the volume of hydrogen gas is still the same. Why? Because the same mass of magnesium is used for both reactions, meaning that magnesium was the limiting reactant. As you can see here, can you please highlight? Okay, and acid was in excess. So the volume of gas collected, okay, volume of gas collected is dependent on the limiting reactant. Okay. Pressure. So now we're looking at how close. So if you recall in the video, right, previously, and the short clip just now, the teacher was pushing the walls of the school closer together. Alright, so that's exactly what we're doing in pressure. When we increase the pressure, we decrease the volume that the particles are allowed to move in. So we're talking about how close are the particles. Alright, so increasing pressure increases the rate of reaction as the particles are closer together. So when the particles are closer together, it will cause to have, when particles are closer together, more particles will occupy that. When particles are closer together, more particles will occupy per unit volume of gas. So which results in a higher frequency of effective collisions. Okay, so now let's look at this diagram. Okay, similar to what the teacher was doing in the clip previously. Okay, at low pressure, the gaseous molecules, or in this case, we'll draw in atoms. Okay, because for simplicity's sake. Okay. At low pressure, okay, I want you to draw, recall in Sec 3 you were taught how to draw particles in gaseous state. So, let's draw it here. Remember, just about perhaps 3 is enough. Okay. Alright, so this is gaseous state. So, at low pressure, it's spread far apart. Okay. So, if you want to go further, you can actually take a ruler and measure the distance between each particle. Now, I want you to also draw it in the high pressure. Make sure it's the same size. Okay. And then I want you to measure the distance between each particle. Okay. You notice that it actually becomes shorter, the distance. Okay. So at low pressure, these particles are basically far apart. And at high pressure, they are closer together. Okay, because they are pushed towards each other. Alright, so as a result, the collisions become more frequent and there's a higher frequency of effective collisions. Therefore, the speed of reaction will increase when pressure increases. Alright. Last but not least, we're looking at particle size. So we're looking at how much is exposed. As you can see in the clip, when I cut down the particle size, when I cut the group open, right, the ones in the center are exposed. So when you decrease the particle size, the exposed area becomes larger. Example. Example, which then results in a higher frequency of effective collisions. Okay, so this is important to note that particle size is inversely proportional to surface area. So this refers to inverse proportion. If a solid is cut into smaller pieces, its exposed surface area gets larger. So more surfaces are exposed for reactants to collide into. So for example, okay, this is cube. If I were to calculate the area, the exposed surface area for this cube, it's 16 cm square. But if I were to cut into 4, the surface area, total surface area becomes 24 cm square. So all in all, when it's a smaller particle size, your surface area increases. Okay, so which results in more reactions taking place in a shorter time, because then the reactants are able, can you see all these arrows? The reactants are able to attack in more area. Okay, so there is higher frequency of effective collisions and speed of reaction increases. So this is another example, right? I would suggest that you copy this down. Okay, the small little circles are particles of liquid, and the big part is the solid. Alright. Okay, so terms used to describe the particle size. So you have powder, you have grains, okay, you have foil, metal ribbon, metal turnings, chips, lumps, and pellets. All this is according to size. So this is the smaller size, and this is the largest size. Okay, please do write this down inside your notes as well. Okay. Now, one thing to note, your particle size, right, affects only solids. Reason being, you can't possibly cut gas or liquids in smaller size. Alright? The only thing that you can cut into smaller sizes are solids. Okay, now let's practice. Okay, again, same question. 5 grams of calcium carbonate was added to 100 cm³ of 0.5 mole per ml of hydrochloric acid. All conditions were kept the same except for the size. So one's powder and one is lump. So which one is bigger? Yeah, this is bigger. Lumps are bigger. This is smaller. Alright, so using collision theory, now let's try to answer this together. I'm able to identify the substance with smaller particle size. So smaller particle size is basically your powder. So calcium carbonate powder has a smaller particle size than calcium carbonate lumps. Next, I'm able to relate particle size to exposed surface area. So recall, particle size is inversely proportionate to surface area. So powder is smaller, so that means its surface area is larger. Next, I am able to state the collisions between particles increasing and decreasing due to the increased exposed surface area. Can you please just excuse the grammar here? Increasing / decreasing. Please make the changes. Okay, so there are more surfaces because increased surface area. So when there's more surfaces, there's more collision. Okay. Then, if there's more collision, there's more effective collision. There is an increased frequency of effective collision. I don't think you can read my handwriting there, so let me try and make it better. Lastly, I'm able to conclude that this results in an increase or decrease in the speed of reaction. So increased effective collision will lead to an increased speed of reaction. Okay. Now, how does particle size then affect the shape of the graphs? Again, smaller pieces means more surface area, which also means more effective collision, which then means faster rate of reaction. So faster means steeper gradient. Okay, can you see the train of thought there? Alright, so gradient is larger at the start for small pieces as compared to large pieces. And the rate of reaction proceeds faster for smaller pieces of solid. So, how does particle size and pressure affect us? So, for example, when you want to cook, okay, let's say I want to cook cabbage. I can't possibly cook one whole big cabbage here, right? You see how sad it looks? Alright, I can't possibly cook this one whole big cabbage here. Alright, it will take very long to cook through. So what we do is usually we'll cut it into small slices. Okay, so it will cook faster. So in summary, there are 4 factors: temperature, concentration, pressure, and particle size. So for temperature, we're looking at how fast. Concentration, we're looking at how many. Pressure, we're looking at how close. And particle size, we're looking at how much is exposed. Okay? Alright, so